So in order to talk about this, we have invited Dr. William Spearman of Liverpool Football Club and Mark Spearman of Project Production Institute. But before we formally introduce them, let's take a moment to set some context for the question. So what are we seeing out there in terms of investment into the world of artificial intelligence, data science, and machine learning? So this is just a few months ago. Worldwide spending on artificial intelligence is expected to double in 4 years, reaching $110 billion in 2024. Nearly 500 AI startups across 42 countries raised over $8.4 billion just in the first quarter. Global machine learning market is projected to grow from 7.3 billion in 2020 to 30.6 in 2024. And specifically in construction market, artificial intelligence will reach 4.51 billion by 2026. So there is no shortage of funding that's being poured into the world of AI and machine learning. Okay. Now, with this tremendous investment, the question really becomes, as Todd posed previously, is what problem are we actually solving? Could we be actually solving a problem that we already know? For example, one of the results that actually was fortunate enough to listen to was the relationship between WIP and cycle time. So after observing many, many data points, they said there is a relationship between WIP and cycle time. And my question was, that's a theory that's been proven mathematically many decades ago. What value did this research actually add? And the question I got is, the answer that I got was, well, it proved that data science works. So again, with this much investment going on and companies actually having a lot of people invested in it, we want to make sure we're solving the right problem. So to do that, to actually have this discussion, let's invite the two experts to give us their views. So first person is Dr. William Spearman. He joined the Liverpool Football Club in 2018 as lead data scientist. From 2015 to 2018, he was data scientist at Hudl. William has used spatial temporal tracking data to identify tactical insights and key moments in football. He has used physics-based modeling to construct visualizable models of open space, pass difficulty, and off-ball scoring opportunities. Before Hudl, William completed his PhD of measurement of the mass and width of the newly discovered Higgs boson at Harvard University through a collaboration with the European Organization for Nuclear Research. And Mark Spearman, Dr. Spearman is the director of PPI's technical committee and technical director at SPS. Prior to his role at SPS, Spearman was the founder and CEO of Factory Physics. During the past 30 years, he has improved operations and increased profits at over 100 companies through the application of operation science. He is a co-author of the book that you guys very well know, Factory Physics, and Factory Physics for Managers, along with numerous other papers. Mark holds PhD in industrial engineering from Texas A&M University, and he's a senior member of IIE. But most of all, he's the proud father of Dr. William Spearman, as you might have guessed. Over to you, Will.
Hi. Thank you for inviting me to speak today. I'm going to be talking briefly here about what is data science and how it's used in a completely different industry, in this case, in soccer. So on to the next slide. This is a quote from IBM about how to define data science, and I quite liked it because it's succinct. It basically states that data science is a multidisciplinary approach to extracting actionable insights from the large and ever-increasing volumes of data collected and created by today's organization. Now, that's nice and succinct, but what does it actually mean? Because in practice, if you ask 100 different data scientists about what data science is, you're going to get 100 different answers. And they're going to usually include buzzwords like AI, machine learning, deep learning, neural networks, recurrent neural networks, convolutional neural networks, et cetera, et cetera. But what does it all mean, and why is it important, and how should it be used? So on to the next slide. I like to talk about data science used in an artful way. So kind of a thoughtful way, rather than just taking the tools of data science and applying them without a lot of thought. So the key elements for me with this are understanding the process, trying to drill down to what is going on at the most fundamental level that's creating the data that you're actually trying to analyze. So if you don't understand the process that's creating that data, or that data is describing, you're going to really struggle to model the data. With that, you can have a directed use of machine learning models. So a deep sense of what the machine learning model is good at and how it can capture that underlying process is going to be important. And given that data science is useless on its own, it's basically a tool for interrogating data and communicating with stakeholders, a focus on intelligibility, especially in a field like soccer, where many of the key stakeholders, like the coaches, the athletes, the analysts, are not mathematically technical. That communication and intelligibility is extremely important. So I like to give this little anecdote because it kind of shows a bad way to approach data scientists, and one that I actually did when I first started working with soccer data. So for those of you who watch soccer, you'll know that after goal, everybody goes and celebrates. So I had access to spatiotemporal player tracking data, and I wanted to build a model that could identify situations that should lead to a goal. And so I used a black box model. I think it was K-Nearest Neighbors or something similar. And it immediately picked up that one of the most dangerous situations in a game is when all of your team is clustered into a corner of the pitch. And if you've watched any soccer, you'll know that that's ridiculous. You would never put all of your players into a corner of the pitch. But moving on to the next slide, one thing you'll notice is that happens after a goal is scored. All the players go to celebrate. So the game is stopped and they're celebrating in the corner. So the model, due to desynchronization in the data, had thought that this was a predictive feature rather than a resulting feature of goal scoring. And this black box model obviously couldn't tell the difference. And so this is what it picked up. So let's look at kind of the opposite of that, which is taking a step back and factorizing the fundamental problems in the process. So soccer is a spatial game of controlling the pitch. And time on the ball equates to control of the ball. So to model that, what you can do is you can actually use an exponential process for controlled touches of the ball, which is a very simple process, incredibly simple math, and then use physics to compute the time it takes each player on the pitch to reach a point on the pitch. And putting that together, you get this visualization on the next slide here, which is what I like to call pitch control. And so this is something that illustrates the locations of the pitch that are controlled by each player or each team. And as you can see, as the defenders here in red converge around a blue player, that reduces the control that blue attacking player has. And so this is nice because it gives us a mathematical, quantifiable way to look at control in a soccer game. And what's particularly nice about this is, even though there's some complex math going into this, this is something that you can show to a coach, to a manager, to even a player, and immediately they can see what this is telling them. Now, the layering part, onto the next slide, comes in where you can take different machine learning models. So for example, what we're seeing here is actually what I call off-ball scoring opportunity. And it's highlighting the dangerous locations on the pitch. So in this case, player, I believe it is 31 there on the left-hand side of the right outside the penalty area. He's got the ball, and he could pass to player 16, who's right near the penalty spot, who is completely open and unmarked, and he would have a pretty easy time to score. So the way we get this sort of off-ball scoring opportunity quantification, which is just a highlighting of this dangerous area, is by combining this pitch control model, which is very bespoke, built around understanding the process, with a transition model, which is a more black box approach, with a value model, which is, again, a fairly bespoke model. And so by layering these different machine learning models, some of which are built at a process level, some of which are more black box, you're able to get a fairly visualizable and intuitive understanding of regions of the pitch that are dangerous at a given point in time. And so with that, I'll hand it over to my father so he can speak about operations science.
Okay, thank you, Will. So there they are. Williams too modest to mention that they won the championship last year, and so very proud of that. So the question is, what is operations science and what does it have to do with data science? Basically, operations science is the science that describes operations, and as you see on the next slide. And if the oil company that Todd had mentioned that optimized the drilling operations, if they had understood operations science a little bit, they wouldn't have done that, because one of the, as Todd pointed out, one of the basic principles of operations science is higher utilization always leads to higher cycle time. But before we get into that, let's talk about what is an operation. An operation is defined as the transformation of entities through the utilization of resources that create or distribute goods and services that satisfy a given demand. The two key terms here are transformation and demand. Without demand, there's no need for the transformation, so you don't have an operation. And without transformation, the demand wouldn't need you if you're the operation, because they would just get it on their own. So whenever we transform anything to satisfy some kind of demand, it becomes an operation. And there's very many of them, as you see on the next slide. Manufacturing transforms raw materials into finished goods. Transformation transforms the location of a part or a package or a person to another place. Medical service transform ill conditions or medical problems into better health. And project execution transforms many different entities into a single object, such as a building or a bridge or an oil platform in the Gulf of Mexico or something like that. So all of these involve demand. Somebody wants a platform in the Gulf of Mexico, and then transformation of resources. So what operations science describes on the next slide is demand processes. How are they characterized? Are they random? Are they constant? Do we know what the demand is going to be? Do we have a good forecast? How does that work? Resource utilization. So there's your two, demand and transformation right there. The resource utilization describes how the transformation occurs. And the utilization tells you how much of the available resources is required. The variability due to randomness and lack of information, variability always decreases the effectiveness, the efficiency of an operation, as you'll see. And that's seen in the buffering and synchronization. Synchronization is talking about how do you synchronize the demand with the transformation. If the transformation occurs before the demand, then you have inventory, you've created stock. If the transformation occurs after the demand, then the demand had to wait for the transformation. And so we call that a time buffer. And so there's two buffers, an inventory buffer, a time buffer. And we learned that if you have more production capacity, then you have demand, then you have a capacity buffer. And the greater the capacity buffer, the less time and inventory buffer you need. That's a key result out of operations science that's not well understood. And when you pull these things all together, you can describe how much work in process is in the production system, the operation, what's the cycle time through the operation, the throughput in the operation is how much is being produced at any point in time. And those things are all related by various operations science relations. And then when you get to stocks, you talk about how much inventory is in the stock. Do we have back orders? In other words, we didn't meet to satisfy the demand, so they had to wait. Or did we lose demand? If a lot of times, if something's not in inventory, then the demand is actually lost. And so what we try to do is, in operations science, we are taking these models and comparing them against actual situations, because as Richard Feynman said, we're trying to make as many mistakes as fast as we can, because that's the only way we learn. And for instance, we had a model, there's a model out of queuing theory, which says the more work in process there is in a system, the greater the throughput. We tested this model with Chevron, an operation at Chevron, and found out that yes, indeed, the more WIP is in the system, throughput goes up to a point, and then throughput begins to go down. That's not predicted by the queuing model. So we had to modify our model and make it better. And so when we did that, we got a better understanding of operations science, and that led to better operations. So operations science is composed of operations research. We use operations research to optimize queuing theory, inventory theory, stochastic models, and of course, big data, because there's lots and lots of data out there. And there's the two of the three curves that Todd was talking about. Now, like artful data science, we want artful operations science. So we don't want to just use black box models of operations research. We want to understand the process, be smart about what to model and what not to, get some good analytics. And then sometimes we actually use basic physics. So data science and operations science both seek to explain how this complex world works. Data science and operations science both require intuition and basic understanding of the next slide, basic understanding of the system, and we don't want to use black box techniques. So the question is it data science versus operations science, or is it data science and operations science? And so how can the production system performance be improved through better combining data science and operations science? So the next slide shows many of the operations science relationships and some of the data science techniques, and these can be used together. We build basically a model of the production system. Using operations science, we come up with some control policies, use data science to explore those control policies to get better execution policies and even execution in real time. And so if we pull it all together, we can use operations science to analyze, optimize, and better understand the system, and then use data science to analyze the complex data. And in real time, we can execute and manage a production system more effectively. Now we have some time for questions.
Mark, and we'll actually have the questions at the end of the panel. Okay.
That's good.
All right, so thank you, Mark, and thank you, Will, for a very enlightening discussion.